You guys see my whiteboard okay?
Yep.
All right, good. I remembered to share this time. Okay, guys, I got 3:30, so let's go ahead and get started. So I'm going to follow up a few lab things with an email just so you guys remember what to do. But basically just a few announcements to make as we go into next week. So obviously your gravimetric analysis results and yellow pages are due on Tuesday since we finished that lab this week. So just a couple things to remember. A lot of people ask, and it's not even in the procedure, but it's just a really good thing to know, and I'll follow it up with an email. It's okay, we got 2 trials, right, of each thing. So we have 2 weighings, right? So we have 2 weighings of each empty crucible, and then we have 2 weighings of each full crucible. Okay, and then you got 3 trials of that. So the question is, well, which weighings do we use? So the best thing to do for a given crucible is to use your final weighings. Use your final weighing empty, and then use your final weighing with the precipitate for each crucible. Okay. So that's generally the best way to go with these things to get you the best possible answer. And over the years, I've found that just gives the best accuracy and precision scores if we do that. So I'll follow that up with an email to make sure you guys get that. So that's one thing. Everybody know what I mean by that? You weighed each crucible twice, right? Twice empty, twice full. So use your final weighing of your full minus your final weighing of your empty, and do that across all 3 of your trials. The other thing to keep in mind for next week is we're continuing on with the kombucha lab. And we have 2 weeks scheduled for it, and I'm going to use the 2 weeks. And I think what I want to do is for the actual analysis of the kombucha, we break that down into 2 parts. So the first part is just to do a regular indicator titration, which is pretty much the very same titration you guys did yesterday. Only now we're going to be using kombucha instead of KHP. All right, so we're going to want to be ready to do that. And then the other part of that is to actually do a pH titration plot and a first derivative plot. So we have to use a pH meter to do that. So we're going to do a single trial using the pH meter. Now, what I think I want to do is when you guys come in next week, I'm going to divide the class into 2 groups, and you'll all come at the same time at the beginning of class and take the quiz like you normally do. But then what we're going to do is I think half of the group is going to do the 4 indicator titrations on the kombucha, and the other half of the group will set up with the pH meters to do that single pH meter titration. And then what we'll do in the second week is we'll just swap those 2 groups. So everybody does all of it just in different weeks. Does that make sense? So in other words, I'll probably have like 6 or 7 pH meters set up. So when you come in, 6 or 7 of you will get on the pH meters and the rest of you will do the indicator titrations. So be ready to do both. And what I'll probably do is go ahead and just break the lab into 2 and give you an idea before you come in of who's doing what each week. So that way you don't have to guess. And if you only want to write up, one part of the lab versus the other part of the lab, you'll know which one to do. So I think that's what we're going to do. And that way nobody should feel rushed at all. It's just that the pH meter titration can actually take a little bit of time. And I don't want you to feel rushed while you're doing it. So that's the primary reason for doing that. Plus we have the extra week to work with. So we might as well use it accordingly. All right, so I'll follow all that up with an email. The only other thing to remember about what we did this week is you should be ready to come in with an average molarity of your sodium hydroxide, because you're going to need that for your calculations. Plus, I want to kind of tabulate it and see how close together your values are. So you'll have your 4, 5, 6 titrations that you did yesterday, however many you did, and you'll have your molarities for each of those titrations for your sodium hydroxide. Then based on those molarities, you'll get an average molarity. So then what I'll maybe have you guys do when you come in is write up on the board what your average molarity is, just so I can see what the variation in the numbers looks like, because I'm just kind of curious about it. All right, so again, I'll follow all that up with an email because there's a lot of information there, but I just wanted to give you guys the heads up. And that email will probably come out tomorrow. Any questions off the top about any of that? Okay, well, again, it's coming with an email so you can digest it then. All right, so let's get back into notes here. So we want to sort of pick up where we left off. And you'll remember that we came up with at the end of class last time a very important expression. And basically, we know that for any conjugate acid base pair, I'm going to write that because that's important. CACB for conjugate acid, conjugate base pair. We know that the Ka for the conjugate acid times the Kb for the conjugate base is going to equal to Kw, which at 25 degrees Celsius is equal to 1.0 times 10 to the minus 14th. Okay, and we saw more or less how to use that last time. Now, I have an example here for propionic acid. I think that's one of the example problems I handed out to you guys on that sheet. So it doesn't matter if you have it or not, that's fine, because I'm going to write everything down here. But basically, we can look at propionic acid. It has the formula of CH3, CH2, COOH. So whenever you see that COOH on there, you know it's a carboxylic acid, right? We talked about those last time. So we could actually draw the structure if we wanted to, like this, put the CH3 and then the CH2 on here, and then show the carboxylic acid group. It's a C double bond O, bonded to an O, bonded to an H. And remember, it's that terminal hydrogen there that's the acidic hydrogen. That's the one that gets picked off by the base, or donated to the base, if you will. Okay, so that's propionic acid. Now, it's got a Ka value, so I can go look that up. And I did, and in your textbook in the appendix, the Ka for propionic acid is 1.34 times 10 to the minus 5th. Right, because remember, for any weak acid, we can look up a Ka in table B, in appendix B. All right, so the question now is, what's the formula of the conjugate base of propionic acid? And then we could also calculate the value of Kb for the base. So the easiest way to do it is just to set it up as an acid-base reaction, so we can kind of see where the proton's shuttling to and from. So we'll go ahead and put our acid down here, CH3, CH2, COOH. Okay. And we'll let that react with water because it's dissociating in water. That's what we always do when a weak acid comes apart. And again, if the propionic acid is the acid and water is going to be the base, then we know that we're going to lose that terminal hydrogen over to the base. So the two things we're going to make are going to be hydronium ion. And we're also going to make the propanoate ion. Propanoate ion is what you call it. It's a CH3, CH2. And I can write it as a COO1 minus. Okay. So you can see what happened there. That hydrogen that I have the arrow pointing at up there on the original propionic acid, that guy right there, okay, that was lost. So see what you have left. It's the carbon with the two oxygens by themselves now. That hydrogen is gone, and notice that the original propionic acid had a neutral charge. So if it loses a proton, it now has to carry a 1 minus charge. Okay, so this would be the conjugate base of propionic acid. Of course, the hydronium ion would be the conjugate acid. Okay, so everybody okay with that? If you wanted to actually draw the structure, you could. It would just be the structure above without the hydrogen ion, but you'd still have that electron pair on the oxygen. And of course, the whole ion would carry a 1 minus charge. Okay, so that's the formula. So now we want the Kb for the conjugate base, which is the propanoate ion. So let's just show what the Kb reaction is, just to make sure that we've got that straight. So again, this is a Ka reaction here because it's the weak acid dissociating. Let's show the weak base reacting in water for the Kb reaction, just to make sure we're all on the same page as to what that looks like. So we're going to start with the conjugate base, propanoate, CH3, CH2, COO1 minus. All right, it's reacting with water. Remember, weak acids and weak bases dissociate in water. Okay, But now this guy's going to be the base and water's going to be the acid. So water's going to pitch the proton back. So we're going to end up making what? Well, propionic acid back again. And of course, we're going to be left with hydroxide ion. And of course, that makes sense because we got a base there. So now the conjugate acid in this case is the propionic acid, and the hydroxide is going to be the conjugate base. Now this reaction is governed by a Kb, and I want to know the value of that Kb. What is it? All right, so again, I've got a Ka. So if we're talking about a conjugate base of that original acid, which is what we're talking about here, we know we've got an equation for that, right? So we know that Ka times Kb equals Kw. I want to solve this thing for Kb. What I'm trying to get, which is Kw divided by Ka. Kw is 1.0 times 10 to the minus 14th. And the Ka was what? 1.34 times 10 to the minus 5th. All right, and if we end up working that out, we end up getting 7.5 times 10 to the minus 10th. Okay, so in other words, if I had propanoate ion in solution by itself, would it be a really strong base or a really weak base, guys?
A really weak base.
Yeah, and you know that because Kb is absolutely tiny, okay? So in other words, this thing doesn't have very much in the way of basic properties. It's going to be a base in solution, but the pH is not going to be very far above 7. Okay, again, that's going to depend to some degree on the concentration of the propanoate you put in there. But based on the Kb alone, no, it's not going to be a very strong base. Okay, so everybody see how to use that equation and when it comes into play? So we can say that, use this equation for any conjugate acid-base pair. So that's very useful for us. So for example, I have a Kb for a base and I want to know the Ka for the conjugate acid, but can't look it up. I could use that equation as well. All right, so everybody all right on that? So let's revisit now some pH calculations. And I say revisit because we've already kind of talked about this a little bit in the context of strong acids and strong bases, but let's just review that. Now, these ones are pretty easy because what do we know about strong acids? So HCl, for example, HCl reacts with water. Do I use a double arrow or a single arrow here?
Single, because it dissociates 100%.
Yeah, so it goes 100% to the right for all intents and purposes. So I'm going to end up making hydronium ion. And I'll get the anion of the acid, which is chloride. Okay. So now pH is easy. Let's say I've got a solution of HCl that's 0.256 molar. All right, so if the reaction goes 100% to the right stoichiometrically, what's the concentration of the hydronium ion in the solution?
0.256 molar.
Yeah, same thing, 0.256 molar. Okay, get 100% conversion of the HCl to hydronium. So now, how do I calculate pH? Well, let's remember our definition of pH from last time. pH is the negative log of the hydronium ion concentration. Should actually have that in brackets because that's meant to be a molar concentration. So in our case, we can go ahead and stick that in there. All right. And what we end up getting when we calculate this out is 0.592. Are my sig figs okay on that?
Yep.
Yeah, I'm good. Because remember what defines the sig figs, right? We end up starting out with the number of sig figs that are in the that are over here to the right of the decimal place. Okay. And then if we get a 0 to the left of the decimal place, we stick with the same number of sig figs. But remember, when we take a negative log of a number, or a log of number for that matter, we have the potential of increasing the number of sig figs because we could end up with a non-zero number here, okay? But in this case, that number is 0, so it remains insignificant. So what does that tell us? Well, it tells us a 0.256 molar solution of HCl is pretty acidic. It's down at 0.592, which is a really, really low pH, which tells me it's a very acidic solution. And that makes sense, okay? And we can do the very same thing with, for example, like a hydroxide base. So I could have like NaOH. Now, the easiest way to show something like this is just to show the base actually dissociating in water. So it goes again 100% to the right. So we just show it dissociating. So we end up just getting a sodium ion. And we get a hydroxide ion. All right, so let's say, for example, I've got a solution of sodium hydroxide that's 0.00139 molar in sodium hydroxide. Now, if we get 100% dissociation, what is the hydroxide ion concentration?
0.00139 molar.
Yeah. Okay, good. So now I want to get the pH of this thing. I want the pH of the solution. So what's a way to do that based on equations I've given you in the past? Do we have an equation that lets us get from hydroxide to hydronium? Well, we do, but there's another way we could do it that I'll show you because a lot of people don't remember this. Okay, so we'll just put a recall here. For any aqueous solution, we can say that hydronium ion concentration times the hydroxide ion concentration are all equal to Kw, which is what, 1.0 times 10 to the minus 14th. Okay, remember that came from the law of mass action for the dissociation, autoionization of water. And we said that for any aqueous solution, that holds true. So one way to solve this problem is I could just solve for the hydronium ion concentration, right? I haven't actually done it here, but we can go ahead and show you how you would set it up. So that's going to equal to 1.0 times 10 to the minus 14th divided by the hydroxide ion concentration, right? So that's 1.0 times 10 to the minus 14th divided by the 0.00139. Somebody's got a calculator handy, you could give me an answer and then we could get a pH out of this if you want.
7.19 times 10 to the negative 12th.
Okay, that sounds about right. Okay, and we'll just keep track of our sig figs here. If the Kw is good to 2, we'll just let that be 7.2 times 10 to the minus 12th. And that's a molar. Now look at that. That's a really tiny concentration of hydronium. Is that kind of what we'd expect in a basic solution?
Yes.
Yeah, you wouldn't expect it to be very high at all because if we have a lot of hydroxide in there, that's forcing the concentration of the hydronium to a very tiny value. Okay, so now it's easy to get the pH. I can just say that pH is just the negative log of the hydronium ion concentration, which is the 7.19 times 10 to the minus 12th. And what do you get?
11.14.
Okay, so in this case, we're good to 2 sig figs over there, but notice what happened. We picked up 2 more sig figs to the left of the decimal place. So that is actually correct to the number of sig figs as I've got there. So we actually went from 2 sig figs to 4 sig figs there because we picked up a characteristic. Okay, so 11.14, that's pretty darn basic and that's what we'd expect because we're dissociating hydroxide. All right, there's another way to do this. And it goes back to this equation I gave you. So let's just go ahead and show you what we can do here. So again, we'll start with that equation. Let me just put a line here so you know what our starting point is. going to take the negative log of both sides of this thing. All right, now here's where the right-hand side's easy. It's just a number, right? So the negative log of 1.0 times 10 to the minus 14th is going to be 14. So we'll get to that in a minute. But what about the left-hand side? Well, this is where we get to use a rule of logs. You guys might remember this identity. If I have the log of A times B, I can write that as the log of A plus the log of B. You guys remember that identity from someplace or another? Trig, algebra, wherever you learn it. So I can apply that here as well. So if I do that, I end up getting the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration. And then that's all equal to 14 because 14 is the negative log of 1 times 10 to the minus 14th. Now, what's another name for negative log of hydronium ion concentration?
pH.
pH. What's another name for negative log of the hydroxide ion concentration?
POH.
POH. Okay, very good. So here's another useful relationship. Okay, so for example, I could have worked the problem above by getting a POH, couldn't I? Because I had a hydroxide ion concentration. There it is. So if I had a hydroxide ion concentration, I could get a POH of that, couldn't I? Let's just go ahead and do it. We should get the same answer. So I want negative log of 0.00139. What do you get when you plug that into your calculator?
Uh, 2.8569, and then we'll have to round that 9 off. So
Okay, that's fine. We'll just underline the 6 there. So that's equal to the POH. That's the POH. It's the negative log of the hydroxide ion concentration. So now, how do I get to pH? Well, I can use that equation up there that says that pH is equal to 14 minus the POH. Okay, so that turns out to be 14, and we won't let the 14 actually limit us. Minus 2.8569. And what do you get?
That would be 11.143.
Is that pretty close to what we got before when we did it? We got
143 with the sig, without the sig.
Okay. So there you go. So that looks like that's about where we want to be. So that's fine. It looks like we picked up a sig fig by doing it that way. But basically, we got the same thing more or less. Okay, so that's just another way of calculating a pH if you have a hydroxide ion concentration. Okay, or the other way, you could also get a POH if you want, if you had a hydronium ion concentration. So we're starting to develop some useful expressions here. Okay, so at this point, it might actually be useful to kind of look at our useful expressions we've got, because we've derived a few of them. Okay, so we'll just say useful acid base. Relationships, how about that? Start with the basic ones and the acidic ones too. pH is equal to the negative log of hydronium ion concentration. pOH is equal to the negative log of hydroxide ion concentration. And there's this other one. We can say that hydronium ion concentration times hydroxide ion concentration. Oh, why is it not right in here? There we go. Is equal to 1.0 times 10 to the minus 14th. Okay, then there's another one we could have. We can derive from that the fact that pH plus POH is going to equal to 14. Okay, so those two are kind of tied together. Now, then there's that other one. For any conjugate acid-base pair, we also know that Ka times Kb is equal to 1.0 times 10 to the minus 14th. That's another very useful one. And then there's a couple others involving Kas and Kbs that we really haven't talked about, but they come up from time to time. And that's this. It's a pKa and a pKb. Now you guys should be able to tell me at this point what a pKa is from a definitions perspective. What would a pKa be?
The negative log of Ka.
Yeah, you got it. Negative log of Ka. And pKb would be what?
Negative log of KB.
Negative log of Kb. Good. Okay. And sometimes in tables, we find Kas and Kbs expressed as pKas and pKbs. Again, so we don't have to use really tiny numbers. Okay, if you're talking about a dissociation constant that's really small. All right, so there's a bunch of useful acid-base expressions that you can apply wherever you need to apply them. Okay, so this will also apply to dynamics too. When you start dealing with acid-base equilibrium there, which you will, these are all useful equations you can use there also. Okay, so believe it or not, you're going to do all this all over again in dynamics. All right, so a couple other things, again, just to be aware of. There's this thing called the leveling effect. And it looks like this. Let's, for example, take a strong acid just for grins here. We'll do nitric acid since we always do hydrochloric. So HNO3 is nitric acid. Let it react with water. You know what's going to happen. The acid is going to dissociate 100% because nitric acid is one of those strong acids that we talked about. So we're going to make hydronium ion. And we're going to make nitrate ion. Okay. So now, let's say I've got, a 10th molar solution of nitric acid. So if I asked you what the concentration of the hydronium ion in solution is, you should be able to tell me, right? It's going to also be 10th molar. And if I had that 10th molar for hydronium ion concentration, now it's easy to calculate a pH from that. Easy peasy. But let's do this. Let's assume that I'm going to take a 10th molar solution of this, and I'm going to dilute it just by adding water. And I could do this through successive dilutions or whatever. But I'm going to take this solution, and I'm going to dilute it all the way down to something really tiny, like 1.56 times 10 to the minus 9th. Right? I mean, we can dilute a solution down as far as we want to dilute it down, can't we? To whatever tiny concentration we want to dilute it to. Okay, so if I diluted it down to that concentration, it would then make sense that the hydronium ion concentration should be the same thing. So let's do a calculation of pH on our diluted solution. Okay, so hopefully somebody has a calculator handy. pH is going to be the negative log of 1.56 times 10 to the minus 9th. What do you get?
8.8068, and that's right. We had 3 sig, so mantissa is, we don't need that 8, yeah.
So we're going to be good at a 6 there. Okay. Now, let me ask you this, guys. Does that make sense? keep in mind what we did. We started with an acidic solution of HNO3 and I just diluted it down to a concentration of 1.56 times 10 to the minus 9. Does it make sense that I should have a pH of 8.8?
Not in the slightest.
It doesn't. That's suggesting a somewhat basic solution, right? So that's what happens. If I get a pH above 7, it suggests I've got hydroxide ion in there, right? Not hydronium, but if I dilute this down, I should still have hydronium in there. So something seems a little bit funny here. Okay, everybody see why that's a funny answer? And it's due to this thing we call the leveling effect. And what the leveling effect says, and it applies to either acids or bases, but let's do it from the point of view of an acid. What the leveling effect says is that you can't dilute an acid. You could put base in here as well, beyond a pH of 7. Okay, so what am I really saying here? Well, what I'm saying is that if I do this dilution and I just continue to add water enough to this to dilute it down, dilute it down, dilute it down, yeah, the pH is going to go up as the concentration of the hydronium goes down, but then I will approach and reach pH 7 and it's never going to go any further on down the scale than that. In other words, it's not going to go beyond a pH of 7. Okay, now, why do you think that might be?
Water's more stable whenever it's not ionized, and so it's the pressure exerted by the acid isn't great enough to overcome the pressure exerted by, I guess, the by water wanting to not be ionized. So we fall to the default to the auto ionization constant.
That's pretty much it. Yeah. So we have to remember that we have this reaction in there as well. And that's defined by KW, right? Now, we did the ice table, remember? And what we found, if we just have pure water in there, we end up with a concentration of hydronium ion of 1 times 10 to the minus 7. Okay? Now, here's the deal. If I'm diluting my nitric acid down to 1 times 10 to the minus 9th, is it really going to matter in the face of the 1 times 10 to the minus 7th that I've got here with regard to the hydronium ion coming from the dissociation of water? Not really. You could say they add together, right? I mean, that's really kind of the best way to think about it. So let's do it as an additive effect, where the pH is actually equal to the negative log of the water dissociation, which gives me hydronium of 1.0 times 10 to the minus 7th, plus the 1.56 times 10 to the minus 9th coming from the other acid. And if you add those two things together and then take the negative log of it, you end up getting like 6.993. I actually did the calculation. Okay. So essentially, I've got a pH of just a little bit less than 7. And it kind of makes sense when I think about it, because now the bigger factor here is the autoionization of the water, because the nitric acid, even though it's a strong acid, is so incredibly dilute, it's a minimal contributor to the overall hydronium ion concentration. Okay, so that's what the leveling effect says. So you can see how that's going to come down to the fact that you can't dilute an acid beyond pH 7, because at some point, you know, the water ionization is going to take over, and that's what the lion's share of the hydronium ion in there is coming from. Does that make sense? So yeah, you had it right. That's pretty much it. All right, any questions about that, guys? So everybody's okay?
Sure.
Yep.
All right, good. Okay, so we've kind of talked about how to deal with strong acids and strong bases. So now kind of the next thing that we have to think about is going to be weak acids and weak bases and how to calculate their pHs. Okay. By the way, guys, I put a new homework up for you guys over at D2L. It's not due for 2 more weeks though. So it's not due this coming Tuesday, but it's going to be the Tuesday after that. But pretty much I think after either this lecture or Monday's lecture, you should have pretty much everything you need to work all the problems. So it's basically covering all the acid-base stuff we've done up till now, and we'll probably finish up on Monday with. All right. So weak acid, weak base dissociation. So the deal here is that when we have a weak acid, for example, now we've got to apply equilibrium steps. And the reason for that, of course, is because the acid is not going to fully dissociate in water. Or if I'm talking about a base, the base is not going to fully dissociate in water. So that means at the end of the reaction, that is at equilibrium, I'm going to end up with a distribution of reactants and products. So anytime that happens, I know I've got to work with equilibrium. Okay, so let's take a look at an example involving an acid. So I think this is a problem that I gave you, but we're going to start out with 0.1526 molar solution of acetic acid. That's HC2H3O2. C2H3O2, there we go. And I want to know 2 things. I want to know in this solution what the pH is. And I also want to determine what the percent dissociation is of the acid. All right. So you guys can see in this situation that the first thing we're going to need to do is to write a dissociation reaction of that acid in water. So let's do that. That's always where we start. HC2H3O2 reacting with H2O. Okay, and by now you guys should be able to predict products on this, right? And we know that's going to be defined by a Ka because it's a weak acid dissociating. What's one product here that I'm going to make?
Hydronium.
Hydronium, good. And the other is going to be the acetate ion, right? That's going to be the conjugate base, C2H3O2. And I got to put a 1- on there, right? So everybody okay with that reaction?
Yeah.
Now, the other thing I can do is go look up a Ka, and I think I've given you a Ka for acetic acid before. And in the table, I think it's 1.76 times 10 to the minus 5th. That can vary a little bit depending on which table you look it up in, but I think I got it out of one of Harris's tables. So I think that should be the same value you guys have or something very close to it. Okay, so if I want to get to pH, let's think about how I have to do this. I need an equilibrium hydronium ion concentration, don't I? So how am I going to get to an equilibrium hydronium ion concentration? What do I have to do?
You have to set up the dissociation. I guess, why can't I think of it? Your equilibrium equation. And
Yeah.
then square root
So
since you have 2 products.
Yeah, so I need I need a law of mass action, don't I? But then to plug the equilibrium values into the law of mass action, what do I need to do first? Remember this?
Yeah, I was making this table.
Yeah, we need an ice table, okay? So anytime we're dealing with an equilibrium situation, I need an ice table. All right, so do I have an initial concentration of the acid? Yes, I do. It's 0.1526 molar. That's how I made it up. Okay. Water. It's pure liquid, solvent, we get rid of it. Now, prior to anything happening, what's my hydronium ion concentration?
Would it be the 1.76 times 10 to the negative?
Nope, that's your Ka. So nothing's happened. This is an initial set of concentrations. Okay, so nothing's happened yet. So what should hydronium be?
0.
0, good. Because we got to let the reaction go to the right. Definitely. So if that one's 0, the acetated is as well. Now, the easiest way to look at this is we could calculate a Q, right? So we can do Qs for these just like we could for solubility products. And if we see that we have nothing on the right, that tells me my Q is equal to 0. So if I were to take these 3 concentrations and plug them into the law of mass action as they are, I'd get a 0, right? 0 times 0 over 0.1526 is still 0. So if my Q is 0, I want to get to my Ka, so that tells me the reaction has to go to the right so I can make some product, okay? So I don't know how much I'm going to make, so I'm going to let that be an X. Now I got to lose X on the left, but I'm going to make a proportional amount of X on the right. And remember, that's coming about because I have 1-to-1-to-1 stoichiometric relationships between all 3 of those things. Okay, so be careful. You'll get back into reactions eventually that don't have that 1-to-1 stoichiometry. And you have to remember then you'd have to use a 2x or a 3x or whatever. Now you add them. Okay, so now we got equilibrium values, don't we? This is an equilibrium value. This is an equilibrium value. This is an equilibrium value because they're in the E line. So let's just remind ourselves what the law of mass action looks like for this thing. Okay, so that's going to be my Ka, and that's going to equal to what? Products over reactants raised to their respective powers expressed as molar concentrations. Do I put water in the bottom?
Nope.
Nope, just the acetic acid. And I got a value for that. That's what, 1.76 times 10 to the minus 5th. All right, so now what do? I plug X's in, right? Oh, I have an X for that. I have an X for that. And then I have this thing over here that goes down here. So what I get is an X squared in the top divided by 0.1526 minus X. And all that's going to equal to 1.76 times 10 to the minus 5th. Okay, so how do I solve that, guys? I mean, there's a few ways I could do it, but what's one way I could solve this for X?
Quadratic.
Yeah, I could set it up as a quadratic. And let's just show that, okay? If we wanted to do that. So now what I would do is I'd have my X squared, and then I have to take my 1.76 times 10 to the minus 5th and multiply that by the denominator. Okay, and then I can distribute, right? So when I do that, I'll get X squared is equal to minus 1.76 times 10 to the minus 5th times X plus that times 0.1526, which turns out to be 2.69 times 10 to the minus 6. And then I rearrange it, right? So I set it all equal to 0. That's what we always do. So I have an X squared plus, because I'm bringing the X term over. And then minus 2.69 times 10 to the minus 6. And all that's equal to 0, right? So now, remember, that's a 1 there. So that becomes A in the quadratic equation. This becomes B in the quadratic equation. And this becomes C in the quadratic equation. Right? Everybody remembers how to do that. So now, I didn't remember it last time. I was trying to put like B squareds and crap in here. X is equal to minus B plus or minus the square root of B squared minus 4AC, right? So I got to raise that to the 1/2 power over what, 2A? So then you just plug your A, B, and C into that and you work it out, okay? And when you do that, you end up getting 2 roots out of this thing. All right, so as it turns out, I don't even have it worked out here. Why? Because I like doing it the other way. Okay, but anyway, that's how we would do it. We'd plug A, B, C, and in there. If somebody does it, we can get the 2 roots. If somebody has them, we can write them down. You guys may even have it programmed in your calculator.
0.00162 163
0.00.
163. Yeah.
Okay. That one kind of sort of makes sense. Okay. I don't know if you have the other root or not.
I didn't do the other one since it doesn't make sense.
Yeah. And then usually what will happen is one root will make sense and the other one won't. So you use the one that makes sense. And I'm just looking at that one right now and goes, yeah, that kind of makes sense. That seems about right. Okay. But remember, when we were talking about this in the context of KSP, and we ended up with a quadratic in 1 or 2 situations there, I had a shortcut we could use. Okay, so let me start by bringing my law of mass action back down again. It's this guy here. So that's my starting point. X squared over 0.1526 minus x is equal to 1.76 times 10 to the minus 5th. So that's my new starting point. Now, here's the deal. I'm looking at this and I'm saying, okay, my K value is really, really, really small, right? It's like 2 times 10 to the minus 5th. So what that tells me back up here in my table is that this reaction is not going to go very far to the right to get to equilibrium because the K is very small. So what does that tell you about the size of X? Is X going to be a big number or a small number? Right? So here's X. That's what we're making. And we just said the reaction's not going very far to the right, right? So would you expect X to be a big number? You expect it to be way greater than 1, or way less than 1?
I have to say smaller.
It's going to be small because the Ka is small. So it's telling me this reaction favors at equilibrium the reactant side. So X is expected to be pretty tiny. So here's the deal. If I've got a really small equilibrium constant like this and X is tiny, look at the denominator here. I've got 0.1526 minus X. Now, if X is a really small number compared to 0.1526, what can I do with that X in the denominator?
Throw it away.
Throw it away. Get rid of it. Whoop, there it goes. Now what have I got? I've got X squared over 0.1526 is equal to 1.76 times 10 to the minus 5th. Now this thing's a whole lot easier to solve, isn't it? I don't have to use the quadratic equation to solve this. Now what I've got is X squared is equal to 0.1526 times my K value, which is 1.76 times 10 to the minus 5th. And if you work that out, I think I have that worked out here somewhere. My X squared is 2.69 times 10 to the minus 5th. You guys can check me as I go. And then what I'm going to do is take the square root of both sides of that. Is it 10 to the minus 6 or 10 to the minus 5th? It looks like it should be 10 to the minus 6, doesn't it? I think it should be 10 to the minus 6. You guys can check me on that. 10 to the minus 5th doesn't make sense. All right. Take square root of both sides of that.
Yeah, it's 10 to the minus 6, not 10 to the
Yeah,
minus.
that makes more sense to me. Take square root of both sides, you get 1.64 times 10 to the minus 3rd. And that's equal to the hydronium ion concentration. Now, how close is that to the value we got when we solved the quadratic equation? We got 1.63 times 10 to the minus 3rd, and this is 1.64 times 10 to the minus 3rd. They're pretty much the same thing, right? So in this case, I'm fine. It looks like I'm fine to go ahead and simplify that mathematically. Now, if those two numbers had varied considerably, then I would say, okay, yeah, that wouldn't work. But I knew I could get away with this because I had like 4 orders of magnitude difference between my initial concentration and my Ka value. So when that difference in those two things exists, I'm probably okay to simplify mathematically and not do this quadratically. Okay. So that's a nice shortcut I can take. And in many situations that we run into, we're dealing with really, really tiny Ka values or tiny Kb values, and we can get away with this little trick. All right, but now let's go ahead and get to pH. So I want pH. So pH is equal to the negative log of the hydronium ion concentration. And right, that's X, isn't it? Go back up to your table. Okay, X is the hydronium ion concentration at equilibrium. So I'm just going to take the negative log of 1.64 times 10 to the minus third. And what do you get? Like 2.785, and that's what I got.
Looks about right.
Yeah, that looks about right. Sig fig's okay? Yeah, I pick up a characteristic there from the original 3. So yeah, should have 4 sig figs. And I got an acidic solution, and that's what I'd expect to get. Okay. Now, just the last thing while we're here is that percent dissociation. That's just another way to couch this. And the way we calculate that is basically we just take the value of X divided by what we started with, okay? So in this case, it's going to be my concentration of either the hydronium or the conjugate base. It doesn't matter because they're both X. And that's 1.64 times 10 to the minus third molar divided by the initial concentration. That was the 0.1526 molar, right? And I wanted to make it into a percent, so I'm going to multiply by 100%. And then what that gives you is about 1.07%. So what that tells me is that in this particular dissociation for this particular weak acid at that specific concentration, about 1 in every 100 of the acetic acid molecules is actually dissociating to give me a hydronium. All right, any questions, guys? All right, I will follow up with that email for you guys as promised. If I don't do it tomorrow, somebody ping me and make sure I do it, because I want you guys to make sure you're doing your calculations correct and you have everything coming to me that you need to have coming to me on Tuesday. But other than that, guys, have a really great weekend and we will catch you on Monday.
All right. Thank you.
You're very welcome.
Dr. Richardson.
Yes, sir.